Hi, welcome to this session. I will be talking about how IVs are handled in the GCM mode, the Kalua counter mode. I will also compare GCM mode and counter mode because there are a lot of similarities, but there are interesting subtle differences between those two modes in particular. So let's get started. The way I wanted to approach is slightly different. I will not go through the document first. I will bring up a problem, and then we will look into necessary parts of the document and take it from there. So I will start with this interesting problem statement. Let's see. Our goal is to find the message 2 corresponding to its ciphertext. Okay. We are also given the plain text for message 1 and its corresponding ciphertext. So this is message 1, A, B, B, B. If you count the number of A's, you should see 16 A's, number of B's, 16 B's, just to make that clear first. And then we are also given the corresponding ciphertext. So the IV is all zeros, and the corresponding ciphertext is here. This is the GCM mode, therefore you also get a tag. So I have also shown you the tag here. Tag is a MAC tag. Okay. What is the ciphertext for message 2? The message 2 has an interesting IV. It's just one more than the IV of message 1. And this is the ciphertext of message 2. And this is the MAC tag for message 2. All right. So what is the question is asking us? The question is asking us, is it possible to find the message? That's an interesting question. It's not us saying that, can you find the message? So let me give you some context behind this. So we got this problem and the data in particular based on this particular program that I will share with you. So here is this little piece of program that is basically, let's walk through this. So this is GCM based. You can see GCM. We have some plain text. In this case, we have the plain text for message 1. This is the plain text for message 2. Even though we know it, I will explain to you the reasoning behind how to reconstruct this message 2. Is it possible at all? Can we reason about it? The AES key size is 256. The key length, that's the key length, 256. ID length was chosen as 16. Tag length is chosen 16. Okay, so let me clarify this one more clearly. The plain text, we are given both the plain text here, although the problem statement says find the second one. That's okay. Don't worry about all these CCCs. The question is, can we get CCCs just based on the given plain text of message 1 and 2 ciphertexts? Okay. So here is the standard template code. Key generation is using AES algorithm. Well, we generate keys for AES algorithm. And then we go through this for loop, which walks through all possible plain texts that are in the array. So in this case, we have just 2 plain text messages. So we have an interesting function called getIV. GetIV is supposed to give us the IV for each message. The index of this loop is used as the argument for the getIV function, which I will show you in a minute. And then we call the encrypt, which encrypts the plain text using the key and an IV. Okay, so we have to look into what is there at getIV function. Okay, getIV function is taking the message ID. Okay, what is message ID? At the beginning, it's 0, right? Because we start the loop with 0. So we create an IV byte array of whatever IV length that was set earlier. We set it to 16. So I is 0 at the very first iteration. So the for loop is completely skipped. We return bunch of zeros as IV. So the first message gets the IV 000. Okay. What about the next message? The next message will have I to be 1, and now it gets a little interesting. Again, we have a IV array made of all zeros. Message ID is set to 1. Now the for loop will run only once. Now we need to look into what is the inc function doing. Okay, so the inc function is basically taking our byte array as an input and increment the byte array by only one value. You know, if the byte array has value 0, it will be incremented to value 1. So it's just a regular increment. Okay, so I don't have to go through all the while loop details, but that's what it is doing. So that's the reason when we ran the code, we got IV's value incremented by 1. You know, the first message gets IV 0, the second message gets the value 1 as IV. Okay, is this a problem or not? We don't know yet. We need to look at how IVs are handled in GCM. But I have shown in my other video that if this algorithm is not GCM but just regular counter mode, then it is clearly a problem. Okay, we can recover message 2 just based on message 1 and the given pairs of ciphertext. Okay, the question now is how the IVs are handled in GCM. So we need to get into a little bit of details to reason about this problem. Maybe one thing we can do is just take the data that we got and reason about it first from a structural point of view. So we have this message made of 2 blocks, right? This is the first block, 16 bytes, and then the whole thing. And then the second block, this part. Okay, so if this was based on the counter mode, we would have easily solved it. What we did in the other video is just took the first message and took the second block of the first message, the ciphertext, which means this part, right? And XOR this with the known part, BBBs, right? These are all BBBs. So we can do that now just to convince ourselves what the outcome of this is. Let's go to the online calculator. Let's take the BBBs, which are basically ASCII, and then take the corresponding ciphertext of the second block of the first message. I'm still talking about the first message, and place it here and do an XOR. Okay. So the XOR is still running, as we can see here. As soon as the XOR is done, I will show you the next step. Okay, we got the XOR of the first plain text second block with the known ciphertext that we got earlier. Now we take the outcome, which is the key stream, right? By XORing the plain text and ciphertext, we get this key stream. We copy this now and make this as the key for the second message, and we take the first block of the second message ciphertext, which is given here, this part, and I place it here, and I will do XOR. Okay, it's showing us some output. I did the similar demo for the counter mode. There, I selected the output to be ASCII format. Let's try the same. Okay, so I did that for ASCII format, but what you see here is a warning message from the tool. It says, the XOR calculator tool, it says there are ASCII characters that are not printable. That really means that something is not okay. We can't basically use the same technique that we used for the counter mode to break the GCM mode. Okay, this raises interesting questions, because if you look at the structure at a very high level, let me show you the structure. This is the NIST document. What they're doing basically is, this picture shows that our IV is treated as a counter, and then the counter is incremented by 1, by 2, and so on. So this is exactly what we saw when we discussed the counter mode also. But there are some interesting differences. It's not really directly incrementing the counter by 1, 2, and so on. It's basically transforming our counter into another value and then increment that value. Okay, so if it was not doing that, we would have gotten the plain text of the second message easily, because the counter value of the first message second block was the same as the counter value of the second message's first block. But it's not anymore true in this case. The reason being that now we get into a little bit of details, how this is going to work. I will explain the algorithm. So whatever IV we are giving from the Java code is not directly used and implemented. What's happening here is slightly different. First, it computes encryption of 0. That's why you see 0 power 128 using a secret key which we don't know. That's the AES key in this case. And then comes interesting point, point number 3, step number 3. It computes the length of the IV. So in my demo, the length of the IV was 128 bit. So it's going to this part. So what it is doing is, it is trying to make sure that the length of IV is a multiple of 128 bit. So we don't need to go through this yes in detail, but that's what essentially it's trying to do. How far am I from a 128 bit? And then it adds enough number of zeros together with the length of the IV, and the IV that we feed in. You see there's a function called GHASH. GHASH is a Galois hash function. So it will transform our IV into another value. So we can get into the Galois hash function in a moment and see how that works. You just can use the search function. Okay, here, almost there. Okay, here it is. So remember, now X is not a plain text. It is our IV together with enough number of zeros and the length of IV. Everything is packaged there in X. So what they do, they chop that X into multiple blocks. The IV is now actually chopped into multiple blocks. And then they do some mathematical transformation that will transform our IV into another value. So this little dot that you're seeing here is basically multiplication in a Galois field. I'm not going to talk about how Galois field multiplication works, but you can imagine our IV and the AES key that was produced through random number generation. The value 0 was encrypted using that AES key. That value is multiplied with our IV to produce some random looking number. So that random number will become the counter. So using GHASH, so what I was trying to tell you is that this is the GHASH function that performs the transformation of our IV into a random value inside the counter block algorithm. And yeah, so picture is better. These x1, x2, xm are not our plain text. So far, they are just our IVs and bunch of zeros, and then the length of the IV, and they get transformed into a final value ym. Okay, and I'll come back to the counter mode in a moment. That value is the value that you see here as J0. Now comes the actual Galois counter mode algorithm. So it's calling now the G counter, right? G counter is a Galois counter. It increments the J0 that we just got it from the hash function, and then calls the encryption algorithm to encrypt the plain text P. Okay, now comes the plain text P that's being organized into multiple blocks and then encrypted using the regular counter mode style. Okay, we can look at the G counter also now. Okay, so G counter is this algorithm. It takes whatever counter value that was coming out of G hash, and then it uses the AES key to encrypt the counter value. That becomes the key stream, and that key stream is XORed with our plain text to produce the ciphertext. So all the Y's that you're seeing here are ciphertexts that encrypts our plain text. Okay, so this is how the G counter is organized. All right, so we can take a step back and reason about why we were unable to apply the same hack we did for the counter mode on the GCM mode. The reason is now clear. Let's go back to the problem statement. The IV of the first message was 0. IV of the second message was 1. But if you count the number of blocks in first message, we have 2 blocks, right? This is made of 2 blocks. All the way until here is 1 block. and this is another block. That means this block is actually encrypted using a counter value, one more than the counter value that was used here. But it's not really using 0 as the counter. It transforms the 0 into what was the output of the GHASH function. So if I can write it here, something like this is happening. So I'm talking about now message 1, right? So counter for message 1 is basically GHASH of ID value. So there are some extra details here, but this is good enough for us. And this counter is the one that is being incremented. So what happens now if you go to message 2? Message 2 is not actually using 1 itself as a counter. Rather, it calls the GHASH of IV. This IV. This is the IV for message 2, but which starts at value 1. GHASH behaves more or less like a regular hash function. Therefore, the output of the counter that you get from GHASH of IV, which is only differing in the least significant bit, right? Here it's 1, and here it is 0. But they will get a completely different counter value. And that's the reason that our trick of just XORing the known plain text with the corresponding ciphertext, produce the key stream, and use that key stream to decrypt the message 2 didn't work. So to sum up, although the counter mode and GCM mode looks pretty similar at a very high level, at the detail level they are different. The counter values are treated in a different way. The user input counter value is transformed into a random number using GHASH, and that counter value is incremented, and then we apply the same structure we followed in the counter mode encryption process. Okay, so another interesting thing to note here is that we can actually play with the IV length. In counter mode, IV length is strictly 16 or whatever block cipher that you're using. If you're using AES block cipher, it requires 16 as the IV length. But in the counter mode, in the GCM mode, you must have, let me rephrase this. In the GCM mode, your IV lengths are a little more flexible. You can have value 12, it will work. So let me reason about what happens when the counter mode is instantiated with IV length 12. So in that case, what's happening here is, let's look into Java code. Maybe it's easier for us to read the code. So when our input is, say, of length 12, when the IV length is length 12, what Java code does is it transforms that into, you see here, expand to one block. It will make sure that the IV is basically made into another 16 byte block. So this part, and then it will use the newly generated padded IV block for counter values. Okay, so that's what's happening here in the expand to one block portion of the code. And what happens now in my case that I have IV length to be 12, just now I modified it to 12. So it will expand it to a 16 byte or 128 bit equivalent. And then it will apply the GHASH algorithm and proceed. Okay. But what happens if your length is more than 16, for example, or equal to 16? So you can actually try with multiple values. You can even try with a 32, which is not a valid value for the counter mode, but it's perfectly fine for GCM. So it works, you get some output, so it's not crashing or something like that. So you can try any value you like. There are some limits, but the program will take care of arbitrary IV length values. Okay. What is the reason and how is this handled? Well, if you look at the way it's handled here, it measures what is the remainder from the ideal block size, and then it will expand it to make sure that you have your IV that is of length multiple of the block size. This portion of the code does that, and then it will use the GHASH function to transform your IV value into a new IV value, which will become the counter. Okay, so this is the interesting subtle difference between how the counter mode handles IV values as opposed to the GCM mode. GCM mode is more flexible, allows you to choose different IV lengths, and it transforms your IV into a unique point using the GHASH algorithm that I briefly talked about. It basically takes your IV, converts it into a polynomial, and performs some mathematics using polynomial operations, and then produce a unique counter value, the value that we saw in the regular counter mode, that kind of thing. So to sum up, you don't want to use, of course, the same IV value for multiple messages. That's the reason why the IV is instantiated inside here in the loop. What you also see here is that you can use simple deterministic way of generating the IV if you want. You know, I have a simple IV value which increases by 1 every time. This is perfectly fine IV value. If you want to have unique IV for each message, this is perfectly fine. However, it's much more easier if you use the regular random number generation, like I talked about in my other demo. Instead of creating IV using get IV function, you may want to use regular random number generation, of course, cryptographic random number generation. Ask for 96-bit random number and use that as an IV. That's much more easier to program. You don't have to remember the state, otherwise you have to know what was the last IV value that you used and so on. That may be extra work, like the code that I wrote here. All right, so to sum up, GCM is more flexible. You can choose different IV lengths you like, more than one, all the way to some very, very large number that's mentioned in the NIST standard. However, it's better to generate the IV value randomly rather than using a deterministic function, which is allowed in the standard. Currently, I'm using a deterministic function to generate the IV value. It still works. It's not easy to break, but it's a lot of extra work for the programmers to generate the IV like this. So I prefer to use random number generation to generate the IV values. Okay, that's all. Thank you very much.